back at Brown, working very hard. He does some really amazing work. He's been working on essentially the early history of Mars, the climate modeling, looking at the interaction of lava and ice, and many, many other things. So he sends his regrets, and a part of his work that we've been working on is, in fact, something totally different from early Mars history, which is the question of did the Orientale melt sheet undergo large-scale igneous differentiation by crystal settling? So who cares about this? Well, it's really an important question. If you take a look at Orientale, most of you know this basin, 920 kilometers, 930 kilometers in diameter. It's beautifully preserved. And we were talking about preservation. I mean, most of these deposits on the moon on the near side, or far side, near side mostly, Imbrium, et cetera, Serenitatis, Chrysium, they're filled with lava, so we have no idea what's going on in the middle. Maybe some of these peaks stick up, but you're not looking at the basic basin. Here, we have it all wonderfully, beautifully exposed. So this is a laboratory for the study of impact basins, and it's not a wimpy one at all. It's a really, really big one from the basin point of view. This is, I think, my favorite lunar orbiter picture, which is a perspective view, and you can get an idea here that actually the ejecta from Orientale alone, this is the Orientale basin, the ejecta comes out to about a lunar hemisphere. Okay, really pretty close to that. So this single event really kind of modified the real estate for about 1/2 the moon in some form or another, say nothing of the seismic shaking. Okay, so the key point here is what was going on in the middle here. We know that craters, fresh craters like Tycho, Copernicus, et cetera, are floored with impact melt. We know the distribution of kinetic energy partitioning into a variety of different bends, if you will, not the least of which is in melting of the target and the destruction of the projectile. So a big question is what happens? How much impact melt is there? Well, we've been looking at the interior of Orientale over the past God knows how many years, because it's such a fertile reservoir here. We know kind of what's going on. And in the early mappers, Macaulay, Wilhelm, Scott Howard, Hodges, et cetera, mapped interior structures here, which were interpreted to be impact melt. And so the question is, gee, how much impact melt is there? We know there's a lot on the floor of Copernicus and Tycho. How much is there in a basin like Orientale? We think there's something of the order of an impact melt sea here, and the reasons are that we can take a look here at the interior of Orientale. This is a topographic map, and you can see evidence for cracking and modification here, which is not so much tectonic, but just cooling of a boundary layer. And when you convert the topography here into what that would be, when you look at the topography and see how much difference there is between the edge of this and the interior, okay, there's offset of over 1 kilometer, and we interpret this to mean that that's the essentially solidification signature, and if it is, approximately 10%, then that means that the thickness of the unit that was cooling and solidifying is about 10 to 14 or 15 kilometers. That's a melt sea, because again, this is several hundred kilometers across easily, and so we're talking about something that's a melt sea. So what happens here if we have an impact melt sea? How long does it take to cool? Is there evidence for differentiation? That is to say, when you take a melt and you solidify it, it doesn't just freeze. Okay, you get things settling out, you get things floating in the terms of plagioclase. So there could be all kinds of differentiation that goes on here, and maybe, in fact, it might tell us something about the interior. Okay, so Will Vaughan, a student at Brown several years ago, took a look at this problem initially, and this is kind of the impact, if you will, the amount of material that's melted from scaling relationships, et cetera, and you have a huge melt cavity, and when the basin collapses, you end up predictably with this impact melt sea. So the question is, what happens to that? What is its volume, first of all? This will give you a little clue as to volume. So this is the Orientale melt sea, about 1 million cubic kilometers. Okay, Stillwater 233, Caspian Sea, Great Lakes, all the way down to a wimpy melt sheet on a 30-kilometer diameter crater. So we're dealing with a lot of material here. And the interesting thing is, when we talk about the assessment of lunar samples, the analysis of lunar samples, sometimes we see anorthosites and other magmatic rocks that are kind of young, like 4.1, 4.2, 4.3. And the question is, how do you get anorthosites and other things that are that young? Well, one option is that you're actually remelting, by impact melting, these kinds of materials. That is, you're taking an ocean, a magma ocean derived product and remelting it to give a younger age. So this has huge implications because you've got a lot of different basins here. And so, if you're adding all up the impact melt for all of these basins, could represent a significant part of the sample collection. That it gives us dates not of the original solidification of the magma ocean, but rather something that happened later on in a melt sheet. We could also maybe getting samples here. If the melt is derived not just from the crust, but the mantle, then we have mixtures of this. And not only that, but it may tell us something, the nature of these impact melts, may tell us something about what the structure of the moon was in the period of time in which these bases were forming. Deborah Hurwitz, one of my students working with David Kring at the LPI, looked at the impact melts in South Polynesian Basin to see if she could distinguish whether or not the event occurred before and after overturn, okay, of the residual part of the magma ocean. So there's all kinds of really important questions here, and all kinds of issues that really need to be resolved to get at these questions and the answers to these questions. So we've been looking at the Orientale Basin. We can start with this scarp here, okay, just to give you a little idea what it looks like inside. This is the scarp right here. It's over between 1 and 2 kilometers here. This is the rough facies of the Maunder Formation, which is interpreted to be a mixture of impact melt and fragments of debris, okay? And this is the smoother portion of the facies here in the interior, and this is Mare basalt on top of it, but the Mare basalt is relatively thin. So we think we have relatively pure impact melt in the interior. This is also critically important for trying to understand the hydrocode models for the formation of these big impact basins. Hydrocode models have become so sophisticated that, in fact, they're really helping us a lot. But there's in my mind anyway, as a geologist, a lot of questions about the terminal stages of the event. The prevailing model right now is published by Jay Malash and his colleagues in Science about a year or so ago, is that in the terminal stages, material comes in over the top, and it's all cooled debris that insulates the thing so that you can then go on in the thermal evolution of the basin to explain the mascons. If it's debris, then that's not impact melt. So, we need to be able to make predictions and test these models because our whole understanding of how these basins form is hanging in the balance, so to speak. So what Will did was to look at equilibrium and fractional crystallization of a variety of different types of targets. And one of the things we were trying to do is predict density profiles so these could be tested with Grail data, for example. So this is a density stratified melt sea, a homogeneous melt sea, equilibrium and fractional crystallization. So there's a lot of options out there, and we can test these in remote sensing data. Paul Spudis and others have tried to do this for Orientale. There's always debate about what hits what and where it is, but again, that's something that's really critical. In some of these configurations, the plagioclase does not form a thick flotation crust, so we can take a look at the predictions there, and then these predictions can be tested. And what we've done is, in fact, try to look at the effects of grain size and cooling time and convection or stratified thermal structure. And so what James has done is essentially set up a model here where we can look at the boundary layer on top, we can look at the diffusion out to space, and look at the gradient here and the change in temperature and viscosity, and look at what settles out as crystals, look at the convecting portion of the magma, and then D is the thermal boundary layer lid. And then we can map this out as a function of time and look at the convection as a function of grain size, okay, size of the individual crystals that are settling out, and ask the question, with vigorous convection, how long does it take to cool, and what does the vigorous convection do to crystal settling and the ability for the magma to differentiate in a significant way? So again, we start with the basic models here, the distribution and predictions, and then we go to looking through a series of quantitative assessments of these parameters. And I won't bore you with this, but the fact of the matter is we can tell essentially the cooling times, and it appears from our initial models, we just submitted a paper to GRL, that the convection is so rapid that for crystal sizes of less of 1 millimeter or less, convection is so vigorous that the settling is not very effective, and so you end up with convection losing a lot of heat and ending up driving the crystallization times to very low values, tens of thousands of years, and in fact not letting differentiation happen because of the viscosity variations, because of the size of the particles, the crystals. So James is, again, if all crystals in suspension settle if the cooling time is greater than a certain time, and the suspended fraction decreases until more crystals nucleate. If the cooling time is less than the critical time, then only some fraction settles and suspended fraction increases. So we can take a look at this real briefly here for Orientale. And so again, the solid fraction, this is for 1 millimeter crystal size. You can see that, in fact, the solid fraction, you don't get a lot of crystallization till you get really close, and then pretty much all of a sudden, in a few thousand years, you get the thing cooling down so that the crystals that nucleate at 1 millimeter or less get frozen in. So you don't get differentiation. And if we take a look here at suspended crystal fraction, for example, if you get 1 centimeter, that'll settle out really fast, okay, because of basically what happens is this helps to retard the convecting aspects, the mixing aspects, so things start to settle out, and that will happen relatively fast. So it's very much a function of grain size. Anything a millimeter or less stays suspended for a long period of time because of the vigorous convection. The vigorous convection cools things fast, and it solidifies very fast. So we find, too, also for Copernicus, that we get similar types of results. So we're testing these right now, and the point here would be that this relatively pure melt in the interior may, in fact, cool very, very fast. And so we need to match this with the Mascon models. They're predicting something very different with a lot of material coming in from the edge. We need to match up what's going on here with the tectonic structures. And then, of course, we need to test all this, these various models with, in fact, observations from remote sensing data. So the bottom line would be convective radiative cooling of the Orientale impact melt sheet occurred rapidly, with solidification occurring in about 10,000 years. Vigorous convection, I got it, inhibits crystal settling of nominally 1 millimeter size crystals, resulting in equilibrium crystallization. And then, of course, predicted to occur for crystal size of 1 centimeter and greater, fractional crystallization and differentiation is predicted to occur. So, you know, in a way, if we could just tell whether there's differentiation, this might help us understand the nature of the convective processes and the grain size during that period of time. Thickness is not predicted to significantly influence, and again, equilibrium crystallization, lunar basin impact melt suggests that about 5% of the crust may have been compositionally homogenized from the adding up the abundances of melt from all these basins. So this is a work in progress. We think this is a new kind of view in terms of the grain size and the rapidity of melting under small grain size configurations, and we're continuing to work on the problem. Thank you very much.
Okay, do we have any questions for Jim?
Just had a quick question about the impactor that caused the basin. Is there any information about the composition or the nature of that object? It seems like such a clean shot. That's, you know, just interesting if we know anything about that.
Yeah. So the question is there any information about the nature and composition? There are scaling relationships which would give you some idea of the size of the thing. So this would be, I don't know, 50 to 100 kilometers, somewhere in there. I should know that off the top of my head. It's about the size of the state of Rhode Island, basically. Composition, yeah. Okay, so with samples, you know, the Highland samples that were taken during Apollo, Ed Anders and his colleagues did really pioneering work in identifying the siderophile elements that could tell you kind of what the parent material were that did that. The trouble was that we didn't know where that particular rock came from. So earlier this week, I talked about a Orientale campaign, okay, to really do the geology and geophysics of Orientale. That would be one of the key things to look for, is to get rocks that came from the central part you could be sure had the material of the projectile, and try to say so. And that's really important because you know, the distribution of impactors. I mean, is this part of the late heavy bombardment, and where did that come from? Or is this part of the NESF model kind of migration? Or, you know, it's not just, oh, it was a X-type meteorite. It's like, oh, that has a lot of implications. A really good point.
Actually, Ross, we're going to have to move on to your talk, so you can hold it for the discussion session. So thank you, Jim.
You can answer it by giving your talk.
There you go.
probably.
Brad Bailey dropped off some liquid